Welcome to the class on E540 Advanced Electromagnetic Theory and Antennas. This will be the second lecture I'll be taking on this course. So in this second lecture we'll be discussing about the electromagnetic boundary conditions. So how many electromagnetic boundary conditions are there? We have 6 of them. 2 electromagnetic boundary conditions for electric field and 2 electromagnetic boundary conditions for magnetic fields and 2 electromagnetic boundary conditions for electric current. So total we have 2 plus 2 plus 2, 6 electromagnetic boundary conditions. So why do we need these electromagnetic boundary conditions? So basically these electromagnetic boundary conditions will explain the behavior of fields. We have both electric field and magnetic field, so that's why electric boundary condition and magnetic boundary condition, and similarly the behavior of current density. So that's why we have electric current boundary condition at the media interface. So what is this media interface? This is basically the boundary between two medium. So let's say you call medium 1 as region 1 and medium 2 as region 2. So the boundary between those two regions is called interface. So we want to find the behavior of fields at that boundary, which is also called as media interface. So now depending on what kind of boundary conditions we are considering, we have electric boundary conditions, then we need to consider the two regions as two dielectrics, different dielectrics with different epsilon. For the magnetic boundary conditions, the two regions should be two different magnetic materials with different mu, and similarly for electric current boundary conditions, the two regions should be two conductors with different conductivity sigma. As we know that the material properties of a material is actually signified by three parameters in electromagnetic field theory. They are epsilon, mu and sigma. What is epsilon? Epsilon is the electric permittivity. It gives you the electric behavior of that material. Mu is the magnetic permeability and it gives you the magnetic behavior of the material, and sigma gives you the conductivity and gives you the behavior of the conductors. So now what we are going to do is we will write down the equation of this 6 electromagnetic boundary condition in scalar form and vector form, and we'll also try to understand what is the statement for each of these electromagnetic boundary conditions. So this diagram actually gives you clearly what is the electromagnetic boundary condition. So what is an interface? Interface is the boundary between two regions, which is shown by a blue line here in the diagram. So now let's say if we consider any kind of vector, it could be electric field vector, it could be current density vector, it could be magnetic field vector. So these vectors are going to have two components. One is tangential component, tangential along the interface, and another is perpendicular to interface, normal component. Tangential component is denoted by T and normal component is denoted by N. So for the electric boundary conditions, the two medium we are considering is medium 1 having epsilon 1 and medium 2 is having epsilon 2. So now here we will find the relations between E1 tangential and E2 tangential. Similarly, we will also find the relation between D1N and D2N. So when we consider the electric boundary conditions, we will find the relations between J1N and J2N and J2T and J1T, which are the tangential and normal components of the current density vector in region 1 and 2. And the two regions would be one conductor with conductivity of sigma 1, another region would be another conductor of conductivity sigma 2. So now for the magnetic boundary condition, we will consider two regions. Region 1 will be having mu1 and region 2 will be having mu2. These are two magnetic mediums, and we will find a relation between the H1T and H2T, and we will also find a relation between B1N and B2N. So let's go to the electromagnetic boundary conditions. First one is the electric boundary condition, and it has to do with the tangential component of the electric fields. So we can write in scalar form simply as ET1 is equal to ET2. So it means that the tangential component of the electric field in region 1 is equal to tangential component of the electric field in region 2. In vectorial form, we can simply write it as n cross E1 minus E2 is equal to 0. N is the normal vector at the interface. We have already discussed that in the previous slide. So now, what is the statement? Statement can be interpreted from the scalar form of the first electric boundary condition ET1 is equal to ET2. So we can write it and we can state it such that the tangential component of the electric field is always continuous across the boundary between two dielectrics. So this is the first electric boundary conditions. Let's go to the second electric boundary condition. It has to do with the normal component of the electric flux density. In scalar form, we can write the equation as dN1 minus dN2 is equal to rho s. What is dN1? dN1 is the electric flux density in region 1 and its normal component. dN2 is the normal component of the electric flux density in region 2. They are not continuous, they are discontinuous. The amount of discontinuity is equal to the surface charge density at the interface. If surface charge density was not present, then this will become dN1 is equal to dN2. If surface charge density is present, then dN1 minus dN2 is equal to rho s. In vector form, you can simply write as n dot d1 minus d2 is equal to rho s. So from the scalar form, we can write the statement for this second electric boundary condition as the normal component of the electric flux density is discontinuous. It's not continuous across the boundary between two dielectrics. And how much is the amount of discontinuity? That is the surface charge density at the boundary. So this is the second electric boundary condition. So let us go to the next electromagnetic boundary condition. It is about the current boundary condition, electric current boundary condition, and it has to do with the tangential component of the current density. So what is the scalar form of this equation? It says that Jt1 by Jt2 is equal to sigma 1 by sigma 2. Jt1 is the tangential component of the electric current density in region 1 and Jt2 is the tangential component of the electric current density in region 2. The ratio of these two is always equal to sigma 1 and sigma 2. What is sigma 1 and sigma 2? Sigma 1 and sigma 2 is the conductivity for the region 1 and conductivity for the region 2. So in vectorial form, we can write as n cross J1 by J2 is equal to sigma 1 by sigma 2. So now the statement you can state it from the scalar form of the first current boundary condition. It basically says that the ratio of the tensile components of the current densities at the interface is equal to the ratio of the conductivities. So this is the first current boundary conditions. Let's go to the second current boundary condition. So it has to do with the normal component of the current density, and in scalar form it can be written as Jn1 or equal to Jn2. So simply Jn1 is equal to Jn2. It says that the normal component of the electric current density in region 1 is equal to the normal component of the electric current density in region 2. They are always equal. In vectorial form, you can simply represent it as n dot J1 minus J2 is equal to 0. And the statement can be interpreted from the scalar form where Jn1 is equal to Jn2. So you can state that the second current boundary condition states that the normal component of the electric current density is continuous across the boundary. So let's go to the first magnetic boundary condition. Boundary condition for magnetic field. So it has to do with the tensile component of the magnetic fields, and in scalar form you can write Ht1 minus Ht2 is equal to Js. What is Ht1? Ht1 is the tangential component of the magnetic field in region 1. Ht2 is the tangential component of the magnetic field in region 2. They are not continuous, they are discontinuous, and the amount of discontinuity is equal to the surface current density at the interface. So in vectorial form you can simply write n cross I1 minus H2 is equal to Js. and the statement can be inferred from the scalar form where ht1 minus ht2 is equal to js. You can state it like this: the tangential component of the magnetic field is discontinuous, it's not continuous, across the boundary between two magnetic materials, and the amount of discontinuity is equal to the surface current flowing along the boundary. Had there been no surface current density flowing along the boundary, then this will be simply ht1 is equal to ht2. So this completes all the electromagnetic boundary conditions. Let us summarize it. We have one more. The second magnetic boundary condition. The second magnetic boundary condition has to be with the normal component of the magnetic flux density, and in a scalar form it can be simply written as Bn1 is equal to Bn2. It says that the normal component of the magnetic flux density is equal to normal component of the magnetic flux density in region 1 is equal to normal component of the magnetic flux density in region 2. They are equal. So you can simply write in vectorial form as n dot b1 minus b2 is equal to 0. So you can also state it from the scalar form. It simply states that the normal component of the magnetic flux density is continuous across the boundary within two magnetic materials. So this completes the all the electromagnetic boundary conditions. Let us review what are the electromagnetic boundary conditions from this diagram. So we have used this diagram at the beginning. Let us try to review all the boundary conditions. What is the first boundary condition? It has to do with two regions, region 1 and region 2, with epsilon 1 and epsilon 2. What was the electric boundary condition for these two regions? At the interface between these two regions, you know that E1t is equal to E2t. The tensor component of the electric field is always continuous, and the normal component of the electric flux density is discontinuous, and the amount of discontinuity is equal to the surface charge density present at the interface. And for the electric boundary conditions, we know that J1n is equal to J2n, and the ratio of J1t with respect to J2t equal to sigma 1 by sigma 2. Sigma 1 and sigma 2 are the conductivities of region 1 and region 2. And for the magnetic boundary conditions, we consider two regions, region 1 and region 2, with mu1 and mu2. And the tensor component of the magnetic field was discontinuous, and the amount of discontinuity is equal to the surface current density flowing at the boundary or interface. But the normal component of the magnetic flux density is continuous. That means B1n is equal to B2n. So this completes the 6 electromagnetic boundary conditions. So this is very much important along with the Maxwell equations. And these 6 electromagnetic boundary conditions, you should be able to explain any kind of electromagnetic phenomenon in the nature. That's all for this class. Thank you.